Good evening to all. This presentation is on the rotor design for an active magnetic bearing supported by wheel rotor. I am only presenting the rotor design part of the full system. I'll briefly introduce the AMB, two working rigs at CSR NAL for active magnetic bearings, overview of the current test rig, objective of the rotor design, how we have gone about to design the rotor, and the conclusion. Introduction and working of the AMB. Introduction: active magnetic bearings provide contactless rotor support. That is their key selling point. They support the rotor from standstill. Unlike gas coil bearings and journal bearings, they don't need a speed to start levitation, and they don't need any lubrication system. And because they don't need any lubrication system, they are very suitable for rotor support in satellites. They have very low losses, so they are suitable for flywheel energy storage systems. They don't contaminate the working fluid, which makes them ideal for sodium pumps, turbomolecular pumps, and organic Rankine cycles. The lubricating oil also doesn't get contaminated by the fluid being pumped. So in that case, that is a specific advantage for wastewater recycling plants. Major disadvantage is that they are complex to design and to install. They are expensive, and there is significant weight and space penalties. Major applications are food and beverage industries, pharmaceuticals, paint industry, semiconductor, wafer processing plants, air conditioners, and wastewater treatment plants. This animation is on the working of a single axis of an AMB. The position of the thrust plate is continuously being monitored by a gap sensor. Gap sensor input is given to the controller. Controller drives the current in the top and bottom actuator to keep the shaft in the reference position. This is one of the test data. This is the initial position of the thrust plate, this plate. Initially the plate is at rest, AMB is switched off. When active magnetic bearing is switched on, the integrator in the PID loop continuously increases the current till the plate starts rising. Once the plate levitates and starts oscillating, the derivative part comes in and stabilizes the plate at the reference condition. This is the TDC of the test rig, bottom dead center of the test rig. This is the reference command, and the plate starts levitation and starts levitating and settles at the reference condition. This condition can be moved up or down by changing the parameters of the closed loop controller. This is one photograph of the radial bearing being developed at NAL. These are the rotor trajectories when the gain of the bearing is changed. Here, as we see, there is a lower limit on the stability. Bearing is unstable, and as gain is increased, bearing is stable, and towards the upper limit of the stability boundary, bearing again becomes unstable. Bearing is stable for all these gain values. In these plots, Kpx is the gain in the horizontal direction, Kpy is the gain in the vertical direction. This is one end-on view of the bearing that is running. This is the active magnetic bearing, vertical axis, horizontal axis, and after levitation, rotor support is contactless. Okay, overview of the current test rig. Weight of the shaft, we are targeting 8.4 kg. Speed is 4000 rpm. Polar moment of inertia is 0.05 kg meter square. O3 is the diametrical moment of inertia. We would target an angular momentum of 22 Newton meter second to get the required energy storage. Position derivative of the bearing is around 33,000. Current derivative is around current derivative is between 9 and 10 Newton per ampere. This is a cutaway of the rig. This is the hollow rotor. This is the flywheel. Here the green part is the flywheel. This U section is the thrust actuator that controls the position in the axial direction. This is the top radial bearing. This is the bottom radial bearing. This animation shows the assembly of the test rig, rotor, flywheel, lock ring for the flywheel, end caps, radial bearings top and bottom, thrust actuator top and bottom, casing, and then excitation. This part I will skip now. This cut section shows the rotor sections. Bottommost section is the bottom turbine mount. Air turbine will be positioned here to rotate the shaft in the test rig. Then there is a section for auxiliary bearing for supporting the shaft in case of sudden power failure. Then there is a section for mounting the balancing bolts. Then sensor target. Sensor needs to target a ferromagnetic area to sense the position of the rotor. Then there is a bottom clearance for routing the wires. Same clearance is given at the top, and in the middle is the actual region where the magnetic bearing supports the load. Same section is there on the top. Same arrangement is there on the top of the rotor. For optimization, these are my constraints. Thrust disc ODN ID should match the thrust magnetic bearing. Pole area should be equal. Radial bearing ID must match the shaft OD. Wall thickness should be at least